So what we're looking at on this question here is this diagram. We're looking at the way that energy is released when electrons are transitioning levels. And so there's 3 different arrows that they have you calculate in this. One of them has 1.174 mega electron volts, one has 2.158 mega electron volts, and the other one is the 1.332 mega electron volts. And so as we're using that, we're using Planck's constant in our calculations here. All kinds of stuff happening. And so on the first drop, the one that's going, when I calculated these, I just went from left to right. And so on this one here, we have the amount of energy that's being released, and we have that in mega electron volts. The equation that we use for energy here that uses Planck's constant needs to be into joules. And so we'll take that number of 1.174 times, it's mega electron volts, so it needs to be times 10 to the 6th. We'll multiply that by 1.60 times 10 to the negative 19th joules is what we have for an electron volt. And so that gives us over here 1.8784 times 10 to the negative 13th joules. Once we have that energy in joules, then we can take and use the equation E equals h times f, so Planck's constant times the frequency. And we can rearrange for frequency, and we'll take the energy that we have in joules divided by Planck's constant. And so we take the energy that we got right up here in our calculation, and then we can divide that by 6.63 times 10 to the negative 34th. Joules times seconds. Joules cancels out, you're left with 1 over seconds, which is hertz. So the frequency of that wavelength that is emitted is going to be 2.83 times 10 to the 20th hertz. It also asks you to solve for wavelength. And you can, the way I chose to do it is by taking C equals F lambda. You could take and use the other equation that's listed in your data book. It has Planck's constant and works through it with to solve for your wavelength. And so I chose to do it this way. So wavelength is the speed of light divided by the frequency. So 3 times 10 to the 8th divided by the frequency that we got. And so it's 1.06 times 10 to the negative 12th meters. So it falls outside of the visible spectrum. However, it can still be an electromagnetic wave that is emitted. Some of them happen to be visible, but not all of them. So in each of these, you're looking at making those calculations, keeping in mind that those transitions have to happen in a full jump that's not spiraling down, and then you can make those calculations from there. Any questions on this part of the practice problems? All right. The next piece we talked about was, or that's in the review, is calculating the mass defect and binding energy. Mass defect, binding energy, and binding energy per nucleon for the nuclei that are given. So boron 10, silicon 28, and lead 207. And so we'll just kind of use one of them. We'll use that first one as an example. And we have, with boron 10, we have 5 protons and 5 neutrons. And so we're taking the 5 protons times the mass of the proton in atomic mass units, plus 5 of the neutrons and the calculation for that. And then we get this top number here. The mass of boron 10 is 10.0129936. So we subtract those two, that gives us our mass defect. So when you're taking the mass of the pieces minus the mass of the nucleus, that's where you get your mass defect. And part of this is knowing the difference between mass defect, binding energy, and binding energy per nucleon. So the next thing we take is we take this mass defect and we figure out how that has shifted into energy. And we know that 1 unit is 931.5 mega electron volts. And so we take the number that we have here times 931.5 mega electron volts for each unit, and we end up with 62.20 mega electron volts. That's our binding energy. That's the energy that has been converted from mass into energy to hold the nucleus together. And then the last piece that we have is figuring out your binding energy per nucleon. And so you take this binding energy that you have and you divide it by the number of nucleons that you have in this nucleus. And so we'll take the 62.20, we're going to divide by 10 because we have 10 nucleons, and it gives us 6.220 mega electron volts per nucleon. And so I didn't write out all of those pieces on the next ones. However, keep in mind that I just used the same colors. So mass defect, binding energy, and binding energy per nucleon. I did that the same here, mass defect, binding energy, and binding energy per nucleon to show each one of these. So you can take a look at those later. Any questions that you have on this, on the process of this, on anything you should know about this? Okay. I think the next piece is about fission and fusion. Yeah, they should be in there. It says explain, draw a diagram, and write equation for the process of fission and fusion. Many variations on this, so choose one for each. Be able to identify the process by looking at the equation. So I will tell you straightforward that you won't have to reproduce this on the quiz, but it's still something that I want you to be thoughtful of and be able to draw and discuss. The biggest thing, the one that is, or there's two main pieces that we're doing with this. With fission, the biggest things about it are that you have a neutron that's bombarding your nucleus. And when that happens, you have to just kind of think about motion and forces and the way that this works. That neutron hits into that nucleus, and in doing that, it makes it more oblong. When it ends up being more oblong, your ends are far enough apart that the strong nuclear force isn't holding them together. The strong nuclear force is holding all these protons and neutrons together. The strong nuclear force is holding all these protons and neutrons together, but it's not holding the ends together. And what's happening with that is that this creates a positive charge. That creates a positive charge because you have protons in both of them. And so then they repel. When they repel, they're going to be in a more stable nucleus. And in order for that, not every neutron can be a part of these nuclei. And so some neutrons are released. They're released with energy in the way of motion. And so then those neutrons then go on and they bombard into another nucleus. And the same process occurs. And so what happens when we're talking about fission, if it's not controlled, for every neutron that's created, a new process occurs. And so if you start with one and then you have three, and each of those go and bombard a nucleus, then three more are released from each one to 9, and 3 more to 27, 3 more to 81, and we would keep going up and up exponentially. And so it ends up being uncontrolled fission, ends up being a really high energy process, and that's where it gets into trouble when you have massive amounts of energy being released and not a way to use it or contain it. And we talk about the parent nuclei is what it starts as, and we say daughter nuclei, they end up being more stable. And then because these are more stable, sometimes they're not super stable. They can continue to go on to decay, but they are more stable than what was happening with the parent nuclei. And because they're more stable, some of those neutrons aren't able to get in there. And so you have neutrons that are released. The biggest thing is we're talking about fusion. And again, there are several different ways you can look at this. Is just that you're dealing with really, really light elements combining. And it rarely happens in a single process. It's usually a chain of reactions that ends at the end with helium and hydrogen. And so this was one that I took and drew out. There's other ways you can do that. We use something like this in the PowerPoint that we were looking at. If you look it up online, there's other ways to do that. But the biggest thing is you're dealing with fission, you're dealing with heavy elements with really large nuclei. And with fusion, you're dealing with really, really light elements for that. And so however you decide to draw that out, there's lots of different examples of equations that you can use. It's just something to be familiar with. Make sure I'm going in order. Any questions about fission or fusion there? So in this next one, it says to determine the amount of energy released in the fission reaction. And I will tell you that if you use the purple pages of your book, it doesn't contain barium-140 or Krypton 93, so you just need to look them up. Look them up online. And if you just type in atomic mass for barium 140, atomic mass for Krypton 93, it'll bring you to a page that will have all the different isotopes. Usually the one that's highlighted, or the one that you've typed in, should be highlighted, and then you can get the atomic mass from there. But what you're doing with this is you're still using the same idea as we are for binding energy. But in this situation, we're taking what's happening at the beginning and how it changes to the end, and then seeing how those masses differ. And so for what we're starting with, we start with a U-235, and we add a neutron to that. So a neutron bombards the U-235. We know that there will be a transitional U-236 in there. It's not what we're going to calculate with what's happening here, because that is very, very unstable. It's only there momentarily, and then this is our final product with the barium 140 and the Krypton 93, and then 3 neutrons being released. And so when you're calculating energy for a fission reaction, you have the mass of the U-235 and the mass of the neutron, and that gives us that 236 number. And then the separate pieces afterward, you have your barium 140, which is the mass is below it, the Krypton 93, the mass is below that, and then 3 neutrons being released. When you add up those 3 numbers, you have 235.867874. And so from what you have, so the mass has gone down, which means that some energy has been released. And so the difference there gives you the mass defect, and then you take that times your 931.5 to get the amount of energy that's released in that fission reaction. So it's very similar to what we do for binding energy, but instead of using your individual protons and neutrons, you're using the particles that you have to start, and then the nuclei that you get afterward, and the numbers that go along with those. So just to make sure that you're not going through and breaking apart completely into protons and neutrons at this point. Any questions on this one? Did not spill any water on myself. All right. The next one is just asking about a half-life curve. And so being able to draw this idea of a half-life curve, a sketch would be fine. And just noting that when you go from what you start with, when you cut that in half, the same amount of time passes each time you go half and half and half. So the time between 100% and 50% is the same amount of time that goes from 50 to 25, is the same amount of time from 25 to 12 and a half. And so that would continue out. Be familiar with being able to figure out just some basic information as you're looking at those calculations and as you're looking at a graph. The IB doesn't require us to go into the detail of using the equation. You're welcome to if you'd like. If you use that in math, or if you've seen it it's in our Holtz book, you're welcome to use that. But a conceptual working through of half-life is what is expected. And so that's what we'll keep our questions as. If you have something that has a half-life of 3.83 days, and we want to know how much has gone by, how much time, how much time has gone by when we get down to 23.4 grams. And so we're starting at 1.5 kilograms. When we go that in half, one half-life has passed to bring us here, another half-life to bring us here, another to bring us here, another to bring us here, another to bring us here, and finally we get down to 0.0234 kilograms, so that would be 23.4 grams. And in order to get to that time, we have 6 half-lives that have taken place. Because we have 6 half-lives and each one is 3.83 days, we can multiply those two to get our total time that it takes to get down there. And that's what I'm talking about with the idea of kind of conceptually being able to work it through and knowing how to work through by literally with your calculator, divided by 2, divided by 2, divided by 2, and counting those half-lives as you go. Any questions on that? All right. And then being able to talk about nuclear radiation. The basic idea is that it ionizes cells by knocking off electrons, and it creates mutations. And so when we're talking about cells and covalent bonds, when you break those covalent bonds and knock off some of those electrons, that cell has been mutated, and if it continues to reproduce, that's where you're getting unhealthy tissue, or you're getting cancers and that type of thing. The radiation or nuclear radiation pros, it can ionize cancer cells, knock those out, break them down, and get them to not continue in the way that they are. For the cons, if it's healthy cells, it causes those to mutate and can cause issues in that way. So when we're talking about nuclear radiation, other pros and cons, nuclear radiation can be used obviously for medical work, and it can help, get rid of things that shouldn't be there within bodies. On a con, if it's used, if you have nuclear radiation and it's released in massive amounts, such as in like a nuclear meltdown or in a nuclear bomb, that's when it starts going in kind of wide scale nuclear radiation. You're going to have a lot of kind of repercussions of that in the way that people's bodies respond. And so those are some of the pieces we're looking for in that. Any questions about that? All right. And then it just talks about going through some of the stuff. That's the last piece I have written here. It says, use the topic 7.3 structure of matter in chapter 7 in the Oxford book to review particle physics topics. So those pages that you did last week, you just did those. And so go through, look at those, figure out, again, just reviewing what happens and how each of those pieces work together. The test that you'll take is similar to the quizzes that we've had. And like I've said before, when we're talking about particle physics and nuclear concepts, the thing that's nice is that we're not dealing with layers upon layers of things. We're looking specifically at some real kind of pinpointed ideas. And so as long as you kind of have gone through the review and have a good understanding of what you're doing in that regard, then you should be in good shape with what you have when you take the test. Other things to keep in mind, actually, any other questions about the review or anything else you want to think about before taking the test?
I had a question about like artificial transmutation. I was wondering, when can you like tell that it is artificial in like the equation as opposed to like fission or fusion?
Yep, so fission and fusion are actually a form of artificial transmutation. Artificial transmutation is a big umbrella that anytime that we collectively, you, me, scientists, anywhere, are causing the process of what's happening. It is the only time it's not artificial transmutation is when it is a decay process. So a decay process, alpha, beta, gamma decay, that's a naturally occurring process. Anytime we go to mess with it, it falls in the way of artificial transmutation. So sometimes we'll see something that'll be specifically, fission or fusion. And usually if I have both artificial transmutation and fission and fusion on a multiple choice, in the wording of the question, it'll specifically say choose the best answer to describe what's happening in the process. And so if you look at it, you're like, oh, this is a fission equation, and fission and artificial transmutation are both listed, then it would be fission would be the correct answer because that's the best one that's being looked at. So sometimes just in some of the other, let me see if I have one here, equations that you just look at and you're like, well, that's not fission, that's not fusion, something's happening, but what? Then that in itself would just be artificial transmutation. So if you look at, let me just look at this real quick. All of the examples that we have up on the top here that we did in that first question, all of those would be just considered artificial transmutation. None of them are dealing with fission, none of them are dealing with fusion. It's just reactions that are happening. They're not decay reactions, but ones that are caused by something that we're doing in the lab. Does that help a little bit?
Yeah, thanks.
I'm glad you asked. I meant to add that one in. Other questions?
Can you explain the difference between a nuclide and an isotope?
Sure. So your nuclide a nuclide is just, sorry, I thought you were saying nucleons. A nuclide is just discussing the It's just saying that it is just the nucleus. That's it. So it's I don't know why they refer to it that way as opposed to nucleus, but it's just saying that it is just the nucleus of that atom. And then your isotope occurs anytime you have a different amount of neutrons. Yeah. Other questions? All right, so things to do. Finish up on your review. Look over the solutions I have up there. If you have other questions that come up, make sure you just send me an email. And then take your test. If your IA is still out, please get it to me. I'm chugging through those, getting them scored up. And what I'll do is I'll post all of them at the same time. So it's not like, oh, you did mine and one person gets it up, another person doesn't. Once I have them all done, I'll get them up. And I will we'll go from there. If you still have your IA, I need to get that. So that's a considerable amount of the score for the quarter. So if you have questions on that, let me know. If you're like, oh my goodness, something isn't going right, let me know. Biggest thing is being able to talk about it. I can't, in school I can be like, hey, what's happening with it, and here there's just not that ability to the same extent. So finish it up, get it into me, get it submitted, and we'll go from there. So if you have any other questions, I'll stay on. Other than that, have an excellent day. If something comes up on the test, let me know. If something's like, oh, this isn't working, let me know. Other than that, have a great day, and I will see you on Thursday. Bye-bye.